Do I have to do anything at this point? Yes. Okay.
You get to sit there and play technique, and I'll come over and help you. So I'll be this chair here, okay. Here, so I'll be back and forth.
Okay.
Good evening. Good evening. Welcome to the Shoals Marine Lab's weekly marine science seminar. I am Sarah Morris, the John M. Kingsbury Executive Director of the Shoals Marine Laboratory, and I want to thank you for joining us this evening for our first Rock Talk of the 2025 season, the 60th consecutive season of the Shoals Marine Laboratory. For those of you joining us online who might be new to our lab community, the Shoals Marine Lab is the oldest and largest marine lab in the country that is focused on undergraduate training, both in coursework and in research. The lab is operated jointly by the University of New Hampshire and Cornell University. Our seminars are affectionately referred to as Rock Talks, in part because back in the early days of the lab, seminars and classroom lectures would often be conducted on the rocks near the intertidal, where the students could then go right into their field work. We've now migrated indoors for these weekly seminars, and they provide a wonderful opportunity for our island community to come together and learn about new and emerging research in topics related to the marine sciences and the environment. In addition to our guests joining us remotely this evening, we have 3 classes with us on the island at this time. Field ornithology, a reprise of biological illustration, ecology. We are also hosting researchers from the Appledore Island Migration Station and the Gulls of Appledore Research Team. We are excited to have everyone both in person and online joining us this evening for this seminar. The seminar format tonight will be a 45-minute talk, followed by 15 minutes of questions and answers. For our friends online, please use the Q&A button at the bottom of your Zoom screen. We will read your online questions out loud for the entire audience. For those of you in the Commons, I will be passing around the microphone for you to ask your questions so that everyone can hear. Tonight's seminar speaker is Valerie Eddington, who is a 4th-year graduate student in the Department of Biological Sciences at the University of New Hampshire. She's a member of both the Ecological Acoustics and Behavior Lab and the Quantitative Marine Ecology Lab, and is co-advised by Drs. Laura Klepper and Easton Wright. Her dissertation focuses on how we can use passive acoustic tools to efficiently monitor large aggregations of animals, including colonial bats and seabirds. She earned her BS in biology from St. Mary's College, where she developed a passion for bioacoustics research. As an undergraduate, she was involved in projects investigating the vocal behavior of small mammals, including the northern short-tailed shrew and fox squirrels. In her current work, she has already published on characteristics of wild moose vocalization, evaluating an acoustic method for estimating bat summer colony counts with audio mouth recorders, and the effect of localized disturbance on the acoustic behavior of the common tern. Today, she was setting up audio moths in the tern colony on White Island and was gracious enough to join us on Appledore as our inaugural Rock Talker for our 60th season. We are very excited to hear her presentation this evening that overlaps with both our field ornithology class and our field bioacoustics and soundscape ecology course. This evening, she will be presenting Beyond the Noise, Studying Colonial Animals Through Sound. Please join me in welcoming Valerie Eddington.
Thank you so much for the introduction, Sarah, and for having me here tonight. And thank you everyone for joining me to listen, talk about my research. So I know, there we go. So I know Sarah mentioned some of the research I did in my undergrad, but since we do have so many undergraduates here, I wanted to just spend a few minutes talking about how I got to where I am today. So during my undergraduate research, I was able to work with a variety of different animals, including northern spurt-tailed shrews. We looked at their ultrasonic vocalization to see if they might be using them to navigate their environment. I spent much time listening to fox squirrels as part of my undergraduate thesis, listening to their alarm calls during the tracking and handling experience. And then I also was able to get involved with a project exploring potential localization of Maasai giraffes in captivity at the Potawatomi Zoo in South Bend. And then I came to UNH originally to study gray bats. So I will have to spend some time talking about bats tonight before I can get to the terns, even though I know that is a large part of why I was asked to speak tonight. I have to give the bats their time in the spotlight. And so when I got out here in the first 2 weeks of graduate school, I was able to come out to Shoals, and as part of the graduate school's orientation, they offered a trip out to see the island. And during that time, I learned about the common tern colony over on White and Seavey Island. And I saw a lot of similarities between the work that I was set up to do with the bats and what issues some of the investigators were running into out on White and Seavey Island. And not only that, the ties between UNH and Shoals Marine Lab offered a really awesome opportunity for collaboration. So I'm really fortunate that this is my 3rd year coming out to Shoals to work with these animals, and I have really awesome collaborators that make it very easy. So I'm very excited to be here today to talk about my research now. So why study acoustics? My goal tonight is to convince you that acoustics is a powerful tool that can augment and in some cases replace traditional methods that tend to be more costly and invasive. So passive acoustic monitoring can enable us to study migration patterns, the health of animal populations and colonies, the behavioral response of animals to disturbance and ecological phenomena, and reproduction. By monitoring populations long term, we're also able to monitor population growth and decline. Long term, we may be able to see responses to climate change. We're also able to get really valuable insights into ecosystem health. So I want to start by asking you guys a question, and you can just shout it out. Why do animals make sound? What is the purpose of their vocalizations?
Navigation.
Navigation, yeah. Communication. More specifically, what are they communicating to each other? What is so important for them to tell each other? Do you have any thoughts on that? Mating. Mating, that's a big one. Fitness, absolutely. That goes hand in hand with mating. Yeah.
What about predators?
Predators, alarm calls are huge, very important. All right. So yes, all great answers. So I just want to start out, when I was in undergrad, this was something that got me really interested in acoustics, learning about how animals communicate. So I thought it would be fun just to share some examples of what the different functions are, as well as some of the really fun sounds that animals make to do these things. So I'm going to start off with one of my personal favorite mating calls, which is the bellowing of a male koala. koalas. Love it. So moving on, someone mentioned this earlier, but anti-predator and alarm vocalizations are also very important for survival. And one of my favorite examples, and I know we have so many ornithologists in the room, so many of you may be familiar with this, is the mobbing call of the black-capped chickadee. So I'll play that for you. And if you ever hear that, I highly recommend you peek around and see if you can spot the predator that they're freaking out about, and also watch them swoop and dive at the predator. It's very entertaining. All right, and then territorial and social calls. So I'm using gray wolves as the example for this because their howls serve both functions, and it is one of my personal favorite sounds. It is just so eerie and so beautiful. And then there are many more purposes that animals produce sound, but the last one I will be talking about here is parent-offspring communication. I'm just going to go right into it. So that was a fawn leading for its mother. So babies will do this to get their parents' attention, to help rescue them from predators, to get fed, or just so they can help find each other after the parent goes off to find it. And so today we'll be talking a lot about passive acoustic monitoring, which is, you'll also see it referred to as PAM. This is a type of remote sensing method that uses autonomous recording units to record and study the soundscape to answer biological questions about animals and to understand how they're interacting with their environment. Essentially, all we're doing is eavesdropping on the animals. And this has many benefits over traditional monitoring in that it is low cost. It enables high spatial and temporal resolution, so we can cover a really wide area in really long periods of time. I know people that leave their recorders out for a full year, and it is absolutely not feasible for us to go spend a full year watching the animals as much as we might like to. It's also minimally invasive, so you don't have to spend quite as much time around the animals, and most often they are not a big fan of you, so this is very great. And it also offers a permanent record of the survey, so we can go back in the future and look back at our data to answer additional questions. You can also have multiple observers look at the same data set to make sure that we're being as accurate as possible. And passive acoustic monitoring is becoming increasingly accessible with advances in recording technology and open source automated analysis techniques. And again, ultimately our goal is to better understand animal behavior to more effectively monitor and conserve populations. And so when we think about analyzing acoustic data, there are two key properties that we are interested in measuring. The first being frequency or the pitch of the sound. So high frequency equals a higher pitch. And I'm going to talk about the three main categories of frequency that we think about. The first being infrasound. So this are frequencies below the range of human hearing. So generally we consider that to be about 20 hertz. And this includes some vocalizations from whales and elephants. Then we have the audible range, which generally is considered to be between 20 hertz and 20,000 hertz, but this does depend on the person. If you have a lot of damage due to going to concerts or listening to music really loud, or just as you age, you start to lose your high frequency hearing. So oftentimes this is closer to 16 or 17,000 hertz. And this includes many, many vocalizations that we are all familiar with, including ungulates, amphibians, birds, insects, all the things that we think about when we go into the forest or into the outdoors and we turn our listening ears on. And then finally, we have the ultrasonic range. So this is above the range of human hearing, generally considered above 20,000 hertz. And most commonly, when we think of ultrasonic vocalizations, we're thinking about echolocation calls from bats and dolphins. The second characteristic we are interested in measuring in our acoustic data sets is amplitude or loudness. And so higher amplitude means the louder a sound, and the standard unit we use to measure amplitude is the decibel, which is on a logarithmic scale. So a 10 dB increase is equivalent to a 10-fold increase in sound energy. And I really like this figure on the screen because it gives some examples of familiar noises that we are used to hearing and approximately how many decibels we could expect them to be. So towards the bottom, around 30 dB, we have a whisper, so pretty quiet. As we move up, we have general conversation around 60 dB. And then when we get up towards the top, around 130, 140 dB is the equivalent to if you were standing right next to a jet engine when it is taking off. So that is incredibly loud. And so I have a couple more questions for you guys. First, using this scale here to the nearest 10 dB, how loud would you expect a cat purring to be? Any guesses?
35.
Very close. Yep, so right around 30 dB. And the next question I have for you guys is how loud do you think a bat echolocation could be? A bat echolocation call could be. And again, these are ultrasonic, so no one here has ever heard a bat echolocation call, which makes this a very tricky question, but just best guess, how loud do you think they can get?
110.
Very close. So bat echolocation calls can be as loud as 130, 140 dB. So I think we are very fortunate that we cannot hear them because they are out all night in the summer echolocating and foraging for food, and we would not sleep very well if we could hear their calls. So just one of my favorite facts about bats. And I want to take a step back and talk about why it's so important that we monitor animals. So animal populations are vulnerable with increased anthropogenic disturbances, and monitoring programs can provide us insight into the behavior and ecology of animals, including trends in population size and insight into phenological events like migration and key breeding behaviors. Monitoring programs also provide us some essential information for informing conservation and management decisions, such as when a system is departing from its desired state, the efficacy of conservation and management decisions, and the effects of disturbances on a population. And unfortunately, many populations are under-monitored or have no monitoring at all. And this can be due to limited resources that conservation groups have to conduct time-consuming and expensive monitoring efforts regularly. And for colonial animals specifically, they often aggregate in difficult to reach places. For seabirds, this includes remote rugged islands such as shoals. And for bats, that can be complex caves, and they also emerge at dusk, and it's very difficult to see them. So we need expensive equipment to be able to see them and get population estimates. So I mentioned earlier that my dissertation research is on 2 species in 2 different taxa, common terns, which are species of seabird, and gray bats. And I know many ornithologists in the room are going to disagree with me on that, but I'm going to make the argument that they are basically the same. So what do they have in common? They're both colonial, so they form really large aggregations. The species that I work with form these colonies for breeding purposes during the summer months. They're both highly vocal, so common terns vocalize to do all of the things I talked about earlier, territory displays, alarm calls, parent-offspring communication, all that good stuff. And the bat vocalizations that I'm interested in are their echolocation calls. They also fly. They're both highly mobile. They're both migratory species, so they form the colonies during the summer when it's warm, raise their babies, and then they head back south during the colder winter months. And they're both very ecologically important in the ecosystems they live and feed in. For my purposes, this is what matters. They're both colonial and they're both highly vocal, which made them prime candidates for the research questions that I'm interested in as part of my dissertation, which is, can we measure changes in the soundscape to gain valuable population insights for large aggregations of animals? And just, if you haven't seen bats roosting before, there are a bunch of individual bats clustered together in there, which would be kind of tricky to see on the big screen. So as I mentioned, before I can get into all of the good stuff on terns, I need to spend a little bit of time talking about bats. So when I came to UNH, my focus was purely on bats. I was interested in how we can use acoustic methods to get population estimates and insights into colony health. And so traditionally, when we monitor bats using acoustics, we're monitoring single bat passes as they fly across a landscape. So if you haven't seen a spectrogram before, that is that big blue blob in the middle of the screen. And so on the y-axis, we have frequency increasing. So the higher up on the axis is a higher pitch. And then we have time going across the x-axis. And I think you guys can see them okay. The little sweeps, the vertical sweeps, are the bat echolocation calls. And so we record these calls as the bats are echolocating and flying across the landscape. And we analyze those individual calls for things like species ID, spatial distribution, and habitat occupancy. And this is useful for many species of bats. And I need your help on the next slide. So I'm going to play a video with some bats flying out of the cave. I need you guys to count them. Can you do that? So I think you guys see my point. It is very difficult to get good population estimates from these really large colonies of bats. So the video I'm playing here is from a Brazilian tree-tailed bat colony, and they can form colonies as large as 20 million bats, which is the largest bat cave in the world in Texas. But more typically, their colonies have tens of thousands, hundreds of thousands of individuals. And for these species, there's really no good way to census these animals traditionally or acoustically. So to continue to demonstrate my point, we have those really nice individual echolocation calls on the left here. And then when we record acoustic data from these really large colonies, it becomes impossible to extract those individual calls that we would use to get estimates of population size. But we do know that there is a whole lot of bats, so we at least have that. And I want to demonstrate something really quick. So can I have 3 volunteers? I promise you don't have to get up. 1, 2, 1 more. Thank you. Okay, so all I need you to do, I'm going to count down from 3. After 3, can you just say hello? All right, 3, 2, 1.
Hello.
Perfect. All right, now we need everyone. When I count down, just say hello. All right, 3, 2, 1.
Hello.
All right, what did we notice? What happened to our acoustic environment? It got louder. Thank you. You just solved my dissertation. So, Klepper et al. 2016 demonstrated that acoustics can predict numbers of bats for extremely dense Brazilian free-tailed bat swarms, essentially proving that there is a predictable relationship between more animals producing a louder environment. And so the figure I have up here is data from those Brazilian free-tailed bat emergences. Each point on this scatter plot is a single second of data showing the number of bats and the amplitude at that time. And you see we have a really nice linear relationship between those two variables, which is great. It demonstrated that this is an effective method and that we can predict numbers using acoustics. However, there was a few limitations with this study. It only looked at a single species at one location. It worked really well at the very high densities. And again, these swarms are incredibly dense with hundreds of thousands of individuals emerging in a short period of time. But it did have poor fit at the lower densities, which you can see as the data begins to spread out a little bit at the bottom. So the goal of the first chapter of my dissertation was to explore the relationship between acoustic energy and emergence density across 6 gray bat colonies. And it's important to note that this is, one, a different species, and they also have different emergence densities. So these are smaller colonies compared to Brazilian free-tailed bats. So it was really interesting for us to explore this question with this group. And to do this, I collected synchronized thermal video data and acoustic data during gray bat emergences at 6 different maternity roosts in Missouri. I also collected some environmental data that we knew could either affect how the acoustics are traveling through the environment or potentially the behavior of the animals. And what I found, agreed with Clifford all 2016, that acoustic energy increases significantly with bats per second. And this is a great example of what real ecological data looks like. So we have a clear trend and we have the statistics to back it up, but there is a lot of variation. And we know that some of that variation is coming from the reporting devices themselves and also just some general differences in site characteristics. And at this point, it's not realistic to have a general model that we could apply to all bat colonies or even to all gray bat colonies. But if we zoom in on a specific cave, we can really start to understand how important our data are. So we were able to find an example in our data set where we collected data at a single location within 1 week using the exact same reporting device. And I'll explain this figure a little bit too. So just like the 2016 figure I showed a few slides ago, each of those points is a single second of data showing the number of bats emerging during that second and how loud it was. And so when we take, so we have 4 different nights, so each color is a different night of emergence. We take all the dots from that night, so all the dots are the same color, and we add those all up. We get the total bats per second and the total acoustic energy produced that night. And when we plot that data for all of the nights we recorded that week, we can see how we can start to make site-specific predictions for locations once we control for our confounding variables. So looking towards the future, what we want to do with this method is translate those trends into a population size to monitor phenology. So hypothetically, if we were able to deploy a recorder at a maternity roost for a full summer, we might see something like this, which shows our acoustic energy over the course of the entire summer during those nightly emergences. I'm going to walk through what we might expect this to tell us about the phenology of the animals. So I mentioned these are migratory bats, and this is a maternity roost. So it's only female adult bats that migrate to this colony to birth their young and raise them. So during this initial period, we would expect the population to go from 0 to some steady number after all of the female adults have arrived at the maternity roost for the summer. Then we have our stable period where the pups are being born, but all of the female adults are there, and they're the only ones leaving the cave each night to forage. And so that's what we're picking up on again, is those nightly emergences. Then once the pups reach buoyancy, which means they're able to fly and go forage themselves, we're going to see an uptick as they're reaching that stage, and then a stabilization again once all the pups have reached buoyancy and they're all doing the nightly foraging with their moms. And then, of course, again, these are migratory. So at the end of the season, we would expect to see a decline as the bats are dispersing for the winter months. And what this would enable us to do is estimate things like birth rate and also the timing of phenological events, which we really don't know a lot about for most of these really migratory species that form these really large colonies. And it's not easy or realistic to do with traditional monitoring methods. So acoustics offers a really great solution that is very easily scalable, so we can deploy widely across many colonies. And again, it's low cost, so it's a really great solution for conservation partners. Okay, so that's it on bats. Moving on, the remainder of my talk will be all about seabirds. And so my dissertation work with the seabirds is using soundscape to monitor population size and breeding phenology in common terns over on what you see next. So seabirds in general are really great bioindicators of the marine ecosystem, and unfortunately, nearly half of all species are in decline. And common terns specifically are a highly migratory and globally distributed species of bird. So up on the top right-hand corner, you can see their global distribution. So these birds are found all across the world, moving north and south for their breeding in the summer. And currently we use visual surveys to monitor these birds to get population data. So this includes point counts, photographic estimation, and drone surveys. However, These survey methods are limited in their spatial and temporal resolution, and they also introduce harmful investigator disturbance to the colonies. And this can increase aggression between individuals as well as nest abandonment, and overall it can decrease colony fitness. So not great. We try and reduce the amount of time we're out there, but we need to spend some time to get some sort of population indicator of the health. And not only that, the time that investigators spend in the colony can bias their ecological and demographic surveys because the birds respond very differently when you are out there in the colony. They're very much not happy that we are out there. Anyone that has spent time in either the gull colony or the tern colony knows they do not want us there. And so I mentioned some of the benefits of passive acoustic monitoring earlier. It is high in its spatial and temporal resolution. It is less invasive, so we just need to put the recorders out and then they can record for a few weeks, even 6 weeks on their own, which reduces the observer bias as well as the investigator disturbance. And again, with advances in technology and more affordable recording units, it's becoming much more accessible. But we're running into the issue of acoustic clutter. So we have overlapping calls, we have tons of individuals vocalizing at the same time. It's very difficult, sometimes impossible, and incredibly time consuming to go through that data to extract individual calls to get some meaningful population information. I'm going to play you an example of what it sounds like in the colony. And this is when there's no people there. So it is much louder when you're in it yourself, but this is what the colony sounds like. How long that was going to go on. So as someone that has spent time out there, it is like that day and night. It is very loud, very noisy. And while it is possible to extract some individual vocalizations, it's not realistic for gaining large scale population information. So we wanted to go back and look at this method that I just talked about with the bats, censusing via acoustic energy, which again, we had explored in bats, but it has not been widely tested in other taxa. Again, the whole concept is that more animals equals a louder environment. And we wanted to see, is this method applicable across taxa? So to do this, I deployed 12 audio mock recorders out on CD Island in summer 2023 and 2024 during the breeding season. I did this in collaboration with Shoals Brain Lab, and they were able to, during their traditional yearly monitoring efforts, collect data for a full colony census and provide me with some detailed phenological information. I've also collected environmental data, including wind, temperature, tide, as well as moon phase, which can be known to affect the behavior of seabirds. My recorders were programmed to record 10 minutes per hour, 24/7, the entire breeding season. I have so much data. And we extracted RMS power, which is just another way of saying acoustic energy or amplitude for 1 minute time windows for our entire data set. And so the first thing I'm going to be talking about is how we might be able to use this to gain information on nest density, which can be used as a proxy for population size. And so the heat map I have here on this figure, for this slide, is showing nest density within 5 meters of each of my recording sites in 2023. And so you can see in the greener areas, that is our higher nest density. And in the purple areas, bluer purple areas, we have relatively low nest density. And then I made the exact same map using average RMS power for each of the sites. And I made a heat map out of it. And so I want to point out some of the similarities between these two figures. So here, circled in yellow, we have areas that have high nest density and relatively high amplitude. Circled in this whitish blue color are areas that have low nest density and are relatively quiet. However, we do have these two edge sites that are particularly different from one another. We have relatively low nest density, but when we look at our acoustic data, it's fairly loud. And so what this is likely due to is high wind and tidal noise exposure at these edge sites. So there's topographical variation in the island, and these edge sites experience much more wind, or at least we believe so. So it's actually why I'm out here right now, is to run some additional tests to see if we can explore this more in the acoustic data to demonstrate that it is indeed wind noise that's inflating our values. And fortunately, we will be able to minimize the effect of this through strategic filtering. So wind noise tends to be pretty low frequency, and the bird vocalizations tend to be a bit higher. So we can manipulate our acoustic data to reduce that wind noise in our data set. And so it takes a long time to process all that data, so I'm working on it, but that is our next step. And part of the motivation with this is not just to see if passive acoustic monitoring is the end-all be-all solution to our monitoring problems, but we really want to explore what is the best way to census these animals. So in collaboration with Liz Craig, Michael Callis, and Frank Sullivan, we are exploring and comparing 3 different methods for censusing these animals. Michael and Frank are drone experts and did some drone censusing of the colony last summer, which you can see here on the left-hand side. So there is an image of the optical camera photo of the terns right next to the thermal video, and it's a bit tricky to see on this screen. Okay, so we do have a couple little specks right here. Those are terns loafing at their nest. And then over here you can see, it's very difficult to see on here, but these little yellow spots, we can see the terns in the thermal imaging through their heat signatures. And then of course we have the traditional visual in-person census that they have been conducting for about 20 years out on Waitangi Island. And we're kind of using that as our ground truth estimate of the number of individuals out there during peak nesting. And then of course we'll be comparing to the passive acoustic monitoring that I have been doing over the last 2 summers to compare these methods, see what their pros and cons are, and hopefully make some sort of recommendation on what the best approach is depending on your conservation and management goals. And then just like with the bats, we're hoping to use this population information to gain insight into their phenological events. And so this is, unlike the bats, real data that I have been able to process from 2023. And we're finding that acoustic energy itself, so the amplitude of the island, gives insight into the breeding phenology of the birds. So starting out, when the birds get to the island, they are participating in courtship behaviors, which have vocalizations associated with them. They're very busy establishing their nests and getting their eggs laid. So we would expect it to be incredibly noisy as these birds are establishing the colony in early summer. So on the bottom axis here, we have the entire breeding season starting from mid-May going to mid-August, and acoustic energy or amplitude increasing on the y-axis. So after the birds have settled on the island, mated and laid their eggs, they are in the laying phase of their phenology, and we expect that amplitude would decrease because they're not spending as much time doing those courtship behaviors, and eggs don't make noise unless you listen really close when they're about to hatch. And then once we get after the laying phase and the chicks are starting to hatch, we would expect that it might start getting a little noisy again. Those chicks are begging for food. The parents and the chicks also use vocalizations to find each other in the colony. And so we see this steady increase in acoustic energy as the chicks are beginning to hatch. And then around when we would expect the chicks to begin fledging, we have a second peak in the amplitude on the island. It's getting loud again. And that again is likely not only due to the chicks begging their parents for food, because they keep doing that all season long, but also because these chicks are beginning to develop their adult vocal repertoires and advance in the sounds that they can make. So it's getting quite noisy again. And then right when we would expect them to start migrating back south for the winter months, we see this nice steady decline in acoustic energy at the end of the season. And not only are we finding this in my data set with the terns, one of my lab mates is also exploring the exact same thing, looking to see if Acoustic energy gives insight into the breeding phenology of Adelie penguins. And so she just defended her master's thesis and found very similar results. I'm not going to go too into the details, partly because I'm not an expert on Adelies, but we do see similar trends in the different stages of their phenology, aligning with differences in amplitude on the island, with this nice steady decline at the end of the season when the colony disperses. And now I'm going to spend the rest of my talk talking a bit about some of the really awesome undergraduate research that's been conducted on this project, starting with the research done by Dan Zogby. And we were really interested in seeing if terns make different vocalizations throughout the breeding season, but no one has described vocalizations in literature quantitatively. So we have all the birder language describing the phonetic vocalizations, but with acoustics, we really need to understand what the parameters are of these calls. So key objective of Dan's research was to quantify the vocal repertoire of the common tern, and hopefully that will give us some insight into if they're actually changing their vocalizations over the summer season, which we would expect they are. And so I'm just going to jump right into the vocalizations that he identified. There's some examples for you guys. And next up, we have the long call. And then we have the kick. And the short PR. And then this next call is what we believe to be a begging call. Again, there's not a ton in the literature that allows us to match up what we're finding in the acoustic data with behaviors, and we haven't had a chance to go out and sit in the colony and scientifically confirm that these behaviors are associated. But this is, again, likely a begging call associated with both population and juvenile begging, but we will need to confirm. And then the last vocalization that we found in our data set is the peck. And this is not a true vocalization, meaning that it's not produced with the larynx, but it is rather a bill clack. So they're smacking their bill together. And this, again, we would need to go out and confirm this through visual observations, but it's likely a warning an attack. Someone that spent time in the colony today, I feel very strongly about that. So they do that right when they're coming at your head. And so what he found is that call types are significantly different from one another by at least one of the parameters that he looked at. Each call type then can be identified based on a specific set of measurements, which is really useful for continuing my work. However, the long call and the short PR are the most similar. So I'm going to play those again just so you can hear how similar they are. They are audibly different, but when we look at the measurements, they're very similar. That was the long call. And that was the short PR. So with this work, we're able to do more effective passive acoustic monitoring in the future and do things like behavioral analyses, how they're responding to us in the colony, hopefully have some visual or video observations to pair with our acoustic data moving forward. And what would be really interesting is we know that some songbird species have regional dialects. It would be very interesting to compare across common tern colonies globally to see if they have similar vocal repertoires or if there are any differences, because seabird vocalizations in general are very understudied. So moving forward, we're looking to compare the vocal characteristics between day and night. That was the original objective of Dan's research, but just measuring the calls ended up being such a task that he never got around to it. So we're going to be doing that this summer. And then we're also looking to quantify the vocalizations of chicks, which have turned out to be very hard to record, but we were able to put out some recorders last summer right in front of the nest. So I have undergrads right now exploring that data. And then I want to talk about investigator disturbance again. So I mentioned earlier, they are very much not happy when we are out in the colony. And our presence can increase aggression between individuals, increase nest abandonment, and overall decrease colony fitness. So I have a video of what it is like for us when we are out in the colony and how the birds are responding to our presence. And so this is a large part of what motivated my research, because we want to try and reduce how much time we spend in the colony to get meaningful population data. But one of the undergraduate researchers that joined me a couple of years ago, Joe Perso, who is now a wonderful seabird technician over on White and Seavey Island, he wanted to look to see if we could use acoustics to monitor the acoustic response of the birds when investigators were in the colony. So he published this research titled "The Effect of Localized Disturbance on the Acoustic Behavior of Common Terns." And so what he was doing was looking at the amplitude at given sites when investigator was occurring in other parts of the colony, as well as in the immediate vicinity. So he looked at this across a gradient of distances. And what he found is that terns have a graded alarm response to investigator disturbance, with investigator presence within 10 meters of a recording site having the most significant and loudest effect on the soundscape. And then between 10 and 20 meters, it was still significant, but slightly quieter. And then beyond that, the response was not significant across sites. So beyond 20 meters, the amplitude of the sites were relatively consistent. So the other thing he wanted to look at, because at this time we did not have that quantified vocal repertoire of the terns to understand what different characteristics were of the different call types, he compared the amplitude at different frequencies to see if we could potentially identify if the terns were making different vocalizations during disturbance and when there was no disturbance. And he found that there was no change in the peak frequency, or where the energy was distributed within the frequency range of the terns during disturbance compared to no disturbance. But again, we do see that overall it is much louder when there is disturbance present than when there is not. And so again, this tells us that common terns have a graded alarm response to investigator disturbance, but what we don't know from this project is whether the terns are increasing the amount of calls being produced, so either the call rate of an individual or the number of birds responding, or if the amplitude of the calls themselves are increasing, which could also be the case. They're getting louder. Individual birds are getting louder when we are out there. And again, the findings do suggest that call types are not changing in response to disturbance, but we would need follow-up research to confirm this, especially now that we have that quantified repertoire with the details of each call type's characteristics. And excitingly, this does support passive acoustic monitoring as an effective tool for colonial seabirds. This was the first paper to come out of our research, so it was really exciting to see that this is working and we are able to get some meaningful information from this. And like I mentioned earlier, this is an ongoing project. So I was out on White Island or on Seavey Island today deploying some additional recorders so that we can explore just how much our sites differ from each other in terms of the soundscape and how those edge sites might be affected by wind more so than the interior sites. And like I mentioned in the beginning, acoustics is a really powerful tool to get a lot of meaningful information on populations and ecosystems. So overall with this project, what we're hoping to do is one, gain fine scale behavioral and phenological information, ideally information on migration patterns, how those are changing with climate change, information on colony health and behavioral responses to disturbance and ecological phenomena, and information on the reproduction patterns. Also with long-term monitoring, we're hoping to get information on population growth and decline, how the population might be changing across the island, response to climate change if we're able to monitor them over a long term, and then also insights into overall ecosystem health, as these birds provide really valuable insight into the system that they forage in as well. I have so many people to thank for helping me make this research possible, especially the folks out on White and Seavey Island who are so great in helping me get those recorders out and maintained over the season. And so many great people to thank for supporting this work financially, especially the school, UNH School of Marine Science and Ocean Engineering, who have supported me over the last 3 summers. And with that, I would like to thank you all for being here and listening, and I'd be happy to take any questions.
So for those of you online, please use the Q&A button at the bottom of your Zoom screen, and somebody will tell me if there's any questions going on. Questions in the room?
Do you hypothesize that there may be a difference in the call repertoire between common terns nesting in colonies with other tern species versus possibly on their own, like colony just common terns?
That's a really great question, and definitely something I've spent a lot of time thinking about. So there are roseate terns that nest over on Seavey Island. Fortunately, they have a clump distribution, so I don't have to worry too much about them affecting my sites, but they are mobile, so it could be possible. I think it would be really interesting to explore that, and I don't know off the top of my head. I do know that they have different vocalizations. People with very well trained ears can tell the difference. I am still working on that, but yeah, I'm not sure. There's so much that we don't know about the vocalizations of seabirds, and I'm very excited that we are finally now starting to explore it. So I'd be very interested to look into that. It's a great question.
Other questions?
Thank you for that. That was really wonderful. I guess a more broader question about passive acoustic monitoring in general. You talk about its limitations. With a population where you can't confirm visually or do not have an extensive repertoire, library of call repertoire, how, if at all, could you extrapolate behavioral information?
Yeah, that would get really tricky, especially if you don't have any background information on the behavior or on the vocalizations that the animals produce. I mean, I think a lot of what my dissertation is trying to get at is just those really broad scale trends, which isn't necessarily behavior, but we are able to hopefully get some phenological information from that. But without visual or some sort of prior knowledge on the types of vocalizations and why they're vocalizing, and more importantly, call rates, like how frequently does one individual vocalize, it would be very difficult to gain any meaningful insights, but that's a great starting point. To start understanding those things would be to just throw out a recorder and see what you hear.
Given the strong nesting territoriality of the terns, does each colony in the New England area have a different dialect?
I want to know. I don't know yet, but that is something I'm really interested in exploring in the future. Again, I mentioned that some songbird species have regional dialects, and I think it would be fascinating to see if seabirds have some of the same behavior, especially with how widely they're distributed across the globe. Yeah, I wish I knew. Hopefully we will know in the future.
You actually addressed one of my questions, but partially with the terns, I was interested in the bats as well. What other variables do you have to deal with for the environmental issues associated with? You've got the sound of the organisms, but then tides make sense to me, but what are you doing with bat caves or anything along those lines?
Yeah, so with the bat caves, we predominantly are recording outside the cave, and that causes a lot of variation between where we are able to set up our equipment and where the bats are actually flying. So that can affect the distance, can affect the amplitude, of course. General cave characteristics can affect the types of behavior they do. So sometimes they are staging inside the cave before they come out, and ideally we're not picking that up, but as I mentioned before, bats are really loud, so it's possible that we're picking up on some of those calls from bats that are not in the immediate view of our camera, which again is what we were using for those counts from our thermal data. So yeah, those site-to-site characteristics that just kind of change how the bats are emerging from the cave is the biggest factor that I would expect. But the emergence behavior of bats is also incredibly understudied. So we don't fully understand how they're changing, how they're flying out of the cave, but also how they might be changing their echolocation behavior depending on the environment and possibly the behavior of other bats.
Yeah, so when you're trying to estimate population size, like for instance with the bats, are you recording? So Sarah's question kind of brought this up, like outside of the cave, is it just the bats that are leaving the cave, and then you're kind of just like timing that for X amount of time, extrapolating, okay, this much frequency is this many bats, and then record over the length of time is how you come up with that number for the estimated population size?
Yeah, so I didn't go into a ton of detail on that for time's sake, but so the way we do it is we have our thermal video camera and our acoustic recorder recording, and bats emerge, colonial bats at least, emerge very synchronized. So most, if not all of the population should be coming out within anywhere between a half hour to an hour and a half. We record that entire period, and then we use those 1 second bins to count from the thermal video how many bats are coming out, and that's what we use as like our ground truth, what we believe to be the true number. And then we're extracting the amplitude, and so we're trying to find some sort of predictable relationship between that. Again, like Sarah's question kind of got at, there's a lot of unknowns that may be affecting that amplitude. Sorry, I'm not sure that answered your question.
Yeah, I was just curious, like.
My question was more just like how you're estimating the population size based on like recording from one point outside of the cave. Like obviously these bats are going to be moving away from there, so is it just over length of time?
Yeah, so the idea is, since all these individuals have to come out to eat, that we're capturing, ideally we're capturing every individual as they pass over the thermal camera. That's our assumption. It's probably not true. We're probably missing some that might be along the edges. Some bats may choose to stay behind if they're able to afford it energetically. But yeah, the assumption is that each bat is being captured on the thermal video.
I'm going to take this question in a different pathway, but if your undergrad self was sitting in this room right now, what would you tell her?
Oh, that's a tough one. I would tell her to have a little bit more confidence in herself and to trust herself that she can do new things and she can do hard things. I have much more confidence today, but I could probably also tell my current self that.
With bats coming out of the caves, do you see echoes a lot on your recordings, and how do you deal with that?
That's a wonderful question. Yeah, echoes are a problem, especially when we record inside the caves, but outside is a problem as well, especially with rocky environments. We get a lot of reflections. So echoes can be weird, and that works in our favor most of the time. in that the echoes aren't always in the same frequency range. So again, this isn't something that I got into very much, but when we're processing our acoustic data for the bats, we filter out energy outside of their echolocation range. So hopefully we are filtering out some of the energy from those echoes, but it's not perfect. We're definitely getting some echoes, but the hope is that the echoes are relatively constant across individuals. And so if that's a constant variable, then it shouldn't be a problem. But yeah, it's a tricky one to deal with, and we have to make some assumptions about that.
Are there any other questions in the room? We're close to the end of time. If not, I would like to ask you all to help me join me in thanking Valerie for such an engaging seminar about the colonial breeding animals and the use of acoustic data to address issues related to population sizes, phenology, and even conservation issues and disturbance. So please thank Valerie for her seminar. We record all of our talks and post them on the Shoals live stream page of our website at shoalsmarineLaboratory.org. For those of you on the island right now, when you leave, you can join us online all summer. And next week, we will welcome Danielle Fibicar speaking on Bats Across Borders, a scientific journey through island bat field work. So we look forward to seeing you next week. Thanks again for attending our first Rock Talk, and thank you, Valerie.